Alright, so we're gonna do that thing where you make a convolutional neural net, and then you synthetically generate a bunch of rectangle data, and then you train the neural net to classify noise versus rectangles, and then and it's not entirely clear that's going to work. You don't really see anywhere in the literature where people are like, yeah, we we trained on noise. So I don't know what that's going to do. And then, I mean, it might not work. But then anyway, if it works, then and we're going to run the classifier in reverse, as you do, to see the true set of images that the classifier actually accepts, because image classifiers, you only train them on like natural images, but once they're trained, they actually, I mean, at least empirically, they accept like huge numbers of images that don't even look like natural images. Okay, so first thing we have to do is get synthetic rectangle data images. And so that's what this is. Like I already wrote that. And they don't look like completely uniform, like the rectangles. They don't look like they're being uniformly distributed around the image, but good enough, right? So then I think the second thing we need is the actual neural net. And so we're using TensorFlow, and Keras within TensorFlow. Does anybody still use TensorFlow? I mean, I feel like everybody uses other stuff, but I forgot how to do this. I think let's see. I mean, does it make sense to use like a functional? I'll just use the thingy where you do this, and yeah. Okay, so we're gonna add some layers to the model, and I think it's just going to be purely convolutional. So, or should I have a pooling layer? Yeah. I mean, I don't really have any strong intuition on how to do this. So we need a convolutional, two-dimensional number of filters. Strides, padding. Yeah. Okay, so number of filters. Does this need? I think this needs an input size. It's kind of like the first thing. Input size? Is that cool? Hopefully. Nah, that doesn't look right. How do you do it? Okay, TF, Keras, sequential. I know there's a way. Oh, input shape. That's what I was looking for. Okay. Alright, so my input shape is... These are batch size of 9, and I guess they're 10 by 10. So they're relatively small, which is good because I'm using like a CPU. I forgot if you need to include the channel. I think you do. So it's like 10 by 10 by 1, right? Like the batch size I think is implicit. And then number of filters doesn't matter. So 16. Padding valid. Okay, so let's just see what this does. So if I run my newly minted neuronal network on my data array, it should do something. Kernel size. I thought that had like a default. Kernel size. Like 3 by 3? Like I thought that was the default, but whatever. Oh no, now it still doesn't like it. Input 0 of layer sequential 1 is in expected minimum number of dimensions equals 4. Yeah. Okay, what if I delete that here? Whoops, here. Is that cool? No. Minimum number of dimensions equals 4. Okay, so it has to have a channel, I guess. So we'll give it a channel and display the 0 channel. Cool, cool, cool. Okay, it finally works. And so we're outputting 9. It's the batch size. 8 by 8 and 16. I don't have any intuition on how this should look, so I'll just do like another layer. I mean, do another convolutional layer. Can't go wrong. You can't go wrong with another convolutional layer. And like 8 filters. Also 3 by 3. So we're now down to 6 by 6. So that's 48. So I guess so like the actual output, you know, we want it to be like a classifier. So we want it to say noise versus not noise. And I think he uses softmax. So I guess we reshape? Do we reshape this one? Maybe. We'll just reshape this layer so that it's like a straight vector, because then we're going to do a dense. Do I need to specify, yeah, like target shape? Yeah. So target shape is, you know, like whatever it should be. Can I just do that? No. Can I do this? Whoops. Oh wow, you can. See, I didn't have to do that multiple, because this is whatever it was 6 times 6 times, I already forgot what it is. Anyway, so then we'll do a dense, and then this will be our net. This will be our net. This is the magic of AI. Okay, so dense units we need 2 units. So these are the classification, the 2 classes. And can I say softmax? Oh, I didn't, yeah, I didn't specify the activation for any of these. So I should probably do that. Okay, yeah, but what is a valid, can you do softmax? Can I just say that? Oh, cool. Okay. So, right. So, yeah. So it's saying like it's 50-50, right? On every one of these images. It's saying 50% probability it's a rectangle, 50% probability that it's noise. Which I guess is good because we haven't trained it. Okay, so I need to go back and specify activations for everything, which I guess is like ReLU. Just gonna use ReLUs. ReLUs are clearly the superior activation. Actually, yeah, I was reading Principles of Deep Learning Theory, and yeah, there's statistical reason that ReLUs work, but I forgot what the reason was. So, all right. Okay, does this all work now? Nice. Okay, this is our neuronal network, and so now we're just gonna train it. You know. Do we need to separate out that code? I guess. I don't know. Oh yeah, what if you do nn dot description? There's a thing for showing compile config metrics. There's a way for showing like the structure, but I do not remember what it's called. So that was a waste of time. Cool. Okay, so we need to train it. So the training is we're gonna do right. So like a good thing with synthetic, well, yeah, I was gonna say a good thing with synthetic data is that your inputs are always novel. I mean, I don't know if that's good or not, but so anyway, it seems like we'll train with batches, you know, like, I don't know, 16, batch size of 16, and maybe half of them will be rectangle classification, and the other half will be noise classification. And so then like an epoch is just, yeah, a number of batches. Okay, so we'll do like 4 epoch in range, you know, I mean, for now, just say 5. You need to like create a batch which I don't know the best way of doing that. Should probably use yeah, like the TensorFlow API, but we are not going to do that. So we're going to copy paste this over. Let's create our rectangles. Actually, like, do these need to be intertwined? you could probably just run it. Yeah, you could just run it twice, couldn't you? So, yeah, right? Yeah? Yeah. Okay. So, yeah. Okay, so we'll get the noise loss. So we run it on a noise batch, and then run it on a rectangle batch. Right? Noise. Okay, so this is the loss for noise. So the noise is just going to be... I also wonder about like normalization of like the noise and stuff. But for now we'll just completely ignore that. And so we'll just make the noise like normal distributed. 0 and 1. So we want it to be the same shape as the rectangles. 10, 1. And the mean, I guess 0. Standard deviation, I don't know, 0.5. And so we run the noise through the neural net, and I think we're just taking the L2 norm of the output with the expected, which is going to be 9 one-hot vectors with the 1 in like the first category. So we're just saying noise is the first category, I guess. So linear algebra norm, yeah. So this, yeah, and then I need to like create the one hot, which I did in my last video, and I forgot how to do it. One hot, perfect. And the indices, on value, off value, depth. Okay, I'm gonna have to play with this real fast because I don't know what that's supposed to look like. Okay, so indices, can I just say 1? No. Indices. Oh, can I say index 0? Like, or blank in range 9? And then depth, I don't know what depth is. Okay, this is a little hard to figure out. Depth 3. Why is it? Oh. Depth 3. Well. No, depth is 2? Yeah. 9 by 2. Okay, now what's the output of the neural net? It is also 9 by 2. Genius. Okay. So do that. Do that. That's okay, so that's the noise loss, and then we do the rectangle loss. Oh, I also need to be doing all of this inside of a gradient tape with tf dot gradient tape as tape. Okay, so then the rectangle loss is going to be adding to run on the array, and the index now needs to be 1. Okay, so I think that's like totally all of that. And then we just update the weights, so we say grads equals tape dot gradient gradient of the loss with respect to the neural net. Do I need to say trainable variables? Maybe. Don't know. Probably. So trainable variables, and then oh yeah, I also need an optimizer. So optimizer equals tf optimizers. Tf dot train Adam? No? Oh no. I don't know where optimizers are located. There they are. Okay. Adam. We always use Adam for no apparent reason. Okay, and then okay, and then opt dot, I think, apply gradients, and then you zip the grads with the trainable variables. Okay, can I kill this? Yeah. So let's print the loss, see if it even works. I have no idea what that means. Linear algebra norm, neural net. This is not good. Oh, this needs to be a subtraction. Don't know why I did it as a comma. This also needs to be a subtraction. Okay. Okay, so the loss goes down, so I'll count that as working. So let's do a few more epochs, and then we'll like test it, I guess. So we'll do like 16 epochs or epochs. Oh no. 16 is too much. Why? Oh, you know what? I also need to... Yeah, these should all be the same cell. There you go. Learned that the hard way. Okay. Because, like, I need to reinitialize if I'm running it twice. Okay, we're getting not a number, which is not cool. Why? Linear algebra norm. Yeah, I don't know why that's happening. Okay, fine. That works. Okay, so let's test it real fast. So, yeah. Generate some noise. And so we're just going to run it on noise. And, yeah, that works, right? Because this, like, these are basically 1 or, well, yeah. Yeah, because the decimal goes back 1. So these are all like 0.99, whatever. And, okay, then run it on rectangles. Ooh, like it's not as high. That's weird. So it's very confident with noise, but it's not as confident with rectangles. Train it longer, maybe. Train it longer. Okay, so we're getting down to 147. And like it's perfect on noise. And it's pretty good on rectangles. I wonder if I should use, I mean, like, I wonder if it makes a difference if you use, what is it, binary cross entropy? Yeah, I don't know how that works though, so I'm just going to ignore that. Okay, so I think we'll do the last thing. So we have like a trained classifier, and so we just want to backpropagate to pixels. And maximize the rectangle output, which is index 1. So we're going to start with an image. I'm going to call these pixels. Oh no. Yeah, random, normal, and so a batch size of 1, and 10 pixels by 10 pixels by 1 color channel, and mean, like, I don't know, 0, standard deviation 0.1, right? So then we're going to backprop, so back in range 10, just, also this needs to be a variable. I don't know if it by default is, but it is now. Okay, so I mean, also we should do like a batch of them, you know. Okay. Okay, now we need to run the pixels. So the loss is just, again, the norm. And again, I should probably use binary cross entropy. I don't know what the difference is, frankly. And, okay, so the neural net run on the pixels versus the one hot output for the category that we want, which is the rectangles are category 1, like index 1. This seems like a stupid way of doing a one hot, but I don't know if I'm doing that correctly. And depth is 2, because there's 2 categories. Yeah. And then you just say, you also need an optimizer. TF optimizers, atom 0.01, whatever. Oh yeah, and we need gradient tape. TF dot gradient tape s tape. Okay, and then compute the gradients using the tape. Gradient of the loss with respect to the pixels, and then you apply. So then you say pixel or optimizer dot apply gradients. And I forget how this works. Oh, it's like a list of pairs. So the grads paired with the pixels, hopefully. And then like print the loss. So see what's happening. Hopefully that works. Oh, it does. And then display the images. Display the images. Yeah, display the images. So, pixels. Oh no. That doesn't look like rectangles at all. What if we do 20 epochs? So it looks like it bottoms out at 1.4 for the loss. And those really don't look like rectangles. What if we do the other category? Which should be noise. Oh no, it gets really low for that. And, print tf dot max value for the pixels, minimum value for the pixels. Doesn't like that. What? Oh, I want reduce max. .4, negative 0.3. It's weird, it can't get lower than 1.4 if you're trying to do rectangles. So if we take these pixels and run them through, .657, which I believe is what it assigns to real rectangle images. Okay, so we kind of have some weird things. One is that, you know, it can basically get perfect, 1.0 for noise inputs, but the max, confidence it can get for rectangles is 0.657. Really don't know why that would be. Do I need more? Do I need more layers? Let's do another layer. Yeah. I guess do 32, 16. I mean, it's completely zero intuition behind it. So then it breaks. Okay, 0.047. Nice. Now that's a low error. So then, oh yes, this is looking very good. We're doing much better. We needed a bigger neural net. So now we're at 0.99 for rectangles and perfect 1.0 for noise. And then if I do my reverse, backprop to pixels, okay, cool. And then it still doesn't look like rectangles though. But it does recognize them as rectangles with very high probability. So, I think that's what we were going for. I mean, so what we learned is that you can take this neural net, which is 4 layers counting the dents, with a softmax output, and you can train it to distinguish from synthetically generated rectangle images compared to random noise. And it can learn that classification, I guess, perfectly. And then if you take the trained classifier and you backpropagate to pixels, trying to maximize the rectangle class output, that seems to train pretty well. And indeed you will find these images that indeed the classifier classifies with 0.99 confidence that they are rectangles. And then if you look at them, if you look at the actual pixels or the actual images, they don't look like rectangles. Let me fix the. Let's do this real fast. Max. So this just fixes the color scale, and now they don't look like rectangles, but they. I mean, arguably they have a lot of straight lines. I mean, you can kind of see like a rectangle here, and then like a rectangle here. But that could just be my eyeballs. Yeah. So anyway, yeah, we'll play around with this some more. What is it about these images that look rectangular? That's the question. I mean, they do have like long, straight lines. So maybe that's what it is. The classifier is basically just looking for long straight lines. Don't know.